So good afternoon and welcome again to the CERIAS seminar. Our speaker today is the person here at Purdue who's had the longest experience with CERIAS other than myself and Marlene Walls, who works with me. Pascal Meunier has been associated with the center for pretty much its entire lifetime. Before it started in the Coast Laboratory, he was involved as a graduate student studying and was one of the first hires into the center as a research scientist. And he's been working with the center ever since. He demonstrates some of the ability of people in other disciplines to gain keen insight into things that go on in computing, having a background not really in computing, but in biophysics, biochemistry, and biology. His PhD is in biophysics. But along a path, which I don't think he'll describe in the talk today, he ended up here at Purdue taking some graduate courses in computing and got enamored of some of the issues in information security and became a full-time passion for him. He's headed up a number of projects through the center over the years. One of the things that he's gotten involved in was where we were trying to establish a more scientific basis for understanding vulnerabilities in software. And he has become one of the more notable members of a collaborative effort that has gone on for many years, spearheaded through MITRE Corporation, to identify and classify vulnerabilities and weaknesses. He's going to talk about part of that today, although there's much, much more he could talk about in the topic area. But I don't want to take any more of his time, so please join me in welcoming Dr. Meunier.
Thank you. All right, so I'll be talking about the common weakness enumeration, which is, as Beth mentioned, directed by MITRE. It's a joint effort with science and security vendors as well. So this is the plan of the talk. I will describe what the common weakness enumeration is. I'll then talk about the top 25. And then I'll move on to what's different in 2010 about the top 25 list. So we'll talk about profiles, we'll talk about mitigations, the metrics we used, guidance, and just to give you an idea of how much effort has gone into this 2010 version, the PDF version of the document is twice the size that it was last year. All right, so the CWE, or the Common Weakness Enumeration, is a unified, measurable set of software weaknesses. For every weakness, we give it an identifier that has the form CWE dash and a number. So the goal is that you can discuss every issue you find in terms of a specific CWE ID. For example, if you run a code scanner, the code scanner can report what it finds with CWE IDs, and then that gives you a reference if you want to find out more about what this type of weakness is and how to mitigate it. You can go look up additional resources. So in the CWE, you have flaws, you have coding errors, you have failures to use mitigations, failure to apply secure programming principles. So in essence, it's an attempt at recording everything that people can do wrong and everything that can go wrong. So it's a blacklist. It's also job security, because as a blacklist, people will always find something new to do incorrectly, or new ways to do things incorrectly. So here's an example of an entry in the CWE. Missing encryption of sensitive data, number 311. So the idea is that you should protect sensitive data when it's in storage or when it's in transit. So the idea is to protect against threats such as packet sniffing, getting your computer stolen, or someone having unauthorized access to read those files. If it's encrypted, it's not going to be much use to them. So I'd like to ask you if you can think of a case where this CWE applies. An example. I'd like to engage you and get you to participate in this talk.
Thing with the video downlink on the predators.
The what, pardon me?
They found that with like home equipment, they could receive the video downlink unencrypted off the predator.
Yes, the drones, right? Yes. So the answer that the gentleman said was that there are some drones used by the army in Afghanistan, for example, that transmit video unencrypted so that, I mean, as a consequence of that, insurgents can look at the video and figure out what's happening and also get more information than they would have otherwise. Here are some other examples. Backups. If you make backups of computers, you'd like your backups to be encrypted when you send them to a storage facility, or if you're sending them on the net to a company, right? There are these companies that allow you to do net backups. So you'd like all that you send to be encrypted. If you store social security numbers or credit card numbers in a database, then you'd like to encrypt those as well in case someone gets access to the database or to the database files. For example, there's standard for the payment card industry, and people demand compliance for it, so it's PCI compliance, and you're supposed to encrypt credit card numbers. You may also want to encrypt your home partition on if you have Unix type operating system or Linux. If you use an application or if you log in over a network, you'd like that to be encrypted while it's in transit. So keep that in mind. I'll ask you a question about this later. So the CWE forms a graph, a hierarchical graph. It goes from very generic issues, and then it spreads out to the more specific ones. It's not, anyway, it's not a pure tree because an entry can have several parents. Okay, entries can also make chains. You can define that before you can use a specific weakness, there has to be another weakness present. For example, there may be in a specific piece of software a buffer overflow that can be exploited only if there's another flaw that allows an integer overflow. An entry may also require other conditions to be present, and then it's called a composite. For example, the CSRF vulnerability. So that's the cross-site request forgery. It's a web development flaw. All right, so the thing is that we have about 800 of those CWEs. And people would like to ask, well, what should we be most concerned about, and what are the hottest weaknesses right now in software? If we conduct an audit, what should we look for? What is most likely to give us the greatest return for our efforts? So this top 25 list gives the most widespread and critical programming errors. So I'll ask you to guess, how many ways do you think there are to overflow a buffer? A, 2 or 3, B, 4 or 5, C, 6 to 12, D, 13 to 25, or E, 50 ways. Okay, it's not E. But well, anybody venture a guess? Pardon me? D? C. Yes. Well, or so I think. It depends on how you count. Because there's this thing called level of abstraction. As I described, it's a hierarchical graph going into more and more details as you go down. So depending on how deep you go, you may get a different count of ways to get something bad to happen. So in this case, if you count the lowest, if you count the leaves, then you should get 8 or 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. And guess what? There are 2 more that we created while making the top 25 list that are not shown in this graph. So you can think about the operation type you're doing, reading versus writing. You can think about the data structure that's involved. Maybe it's an array, maybe it's a string. Maybe you're not checking for the size. Maybe the size of the buffer that you need is not calculated correctly. So there are many aspects from which you can look at a weakness. So the level of abstraction matters. There can be so many ways for some types of weaknesses that it's hard to remember them all. So the idea this year was, we said, if we list things that are very high level, people will think that they have covered all the more specific forms of the weakness, but there's a risk that they'll forget 1 or 2. So in 2010, we used lower level CWEs in the top 25 list. So for example, instead of just stating generic buffer overflow, we'll use CWE 131, which says that you use an incorrect calculation for the buffer size. We also wanted to avoid something that could happen, that is having both a parent and a child in the list. So it happened, we noticed that there were some entries that we were forced to include on the list because we didn't have a lower level CWE. So we created more CWEs to provide a consistent level of abstraction in the list. Another thing we did, because we're using lower level, we need more space. Okay? So we took some general good practices that were very high level, but instead of removing them from the list, we created a special section called mitigations. For example, last year we had this CWE 20, improper input validation, right? Everybody knows they should do input validation, or we hope anyway at this point. So that's being moved to the mitigation list. It's a first mitigation: establish and maintain control over all your inputs. So this is a list of the new CWEs we needed for the level of abstraction we chose. For example, CWE 798, the use of hard-coded credentials. Right? For example, there are things that ship with hard-coded passwords in the firmware, backdoors. Other things that are hard-coded credentials, keys for DVD players. Those are hard to change. Pardon me?
Routers.
Routers, yes. And so forth. To rank the issues, we use importance instead of severity. Because last year we were concerned about severity. So by using importance instead of severity, we don't have to be limited to CWEs that will cause huge damage immediately. So we can include something that gives information, valuable information to hackers. So when there's an error message, there are many systems that will give you detailed information about the tables used in the database, which script was running, maybe even which user ID it was running as. And all those things can be very helpful for an attacker. We also did formal voting and scoring. Because last year what we had was a kind of sponsorship. People said, I believe this CWE is very important. It should be included in the list. So that was subjective, depending on how convincing someone could be. But in 2010, we used two criteria, importance and prevalence, and we gave them score. And then after we have these two ratings, how do we sort the entries? So we have importance and prevalence. You could take the square of each and add them, or you could multiply one by some scaling factor. But risk is defined as the potential loss multiplied by the probability of occurrence. So it makes it a natural fit that you'd think of ranking the entries in the CWE by importance multiplied by prevalence. There were some issues in the ratings. So think about this CWE here. Download of code without integrity check. So if you're going to run code on your system, you want to make sure that nobody stepped in during the transfer and substituted or inserted their code in the middle, right? So if you're doing an update of your operating system, the download of the new code is all encrypted, or should be. The modern operating systems now all have encrypted downloads. However, think of JavaScript. It's all over the place. In Facebook, it's very difficult now to access a website with JavaScript turned off. So you download JavaScript, which is code that is going to run on your machine in your browser, but most people aren't concerned about trying to encrypt it. So one reason for that could be that it's executing in a restricted environment, right? So the risk is lower. So for this CWE, depending on the context you choose, whether you're thinking about JavaScript or critical updates, the ratings are different. Now with prevalence has problems too, because we only know about what's been found. On top of that, people researching vulnerabilities research what they feel like. So they can be capricious. They can want to report on hot things and not do it systematically. That leads to peaks in prevalence during certain years, and then the next year there's nothing, and then the next year then there's again some more vulnerabilities found of the same type. Then there's limited manpower to process discovered issues, to look everywhere for all sorts of information, everywhere in the world about someone finding a vulnerability. So some don't make it into the list of known vulnerabilities. And then the best ones are kept secret. We don't even know about them. They're sold on a market. They can be sold to government agencies. They can be sold to companies. There are companies offering bounties for that. We had a speaker earlier at the security seminar who was describing how they purchased vulnerability information from researchers. So we don't know about all of these. So to find prevalence, we used these sources. We used the common vulnerability and exposures enumeration, which is another effort by MITRE. We used also data from security vendors. And we also used personal experience and judgment, which is a little bit more subjective, but when there is no hard data on the prevalence of some weaknesses, that's what we had to use. Now, that sounded like a great idea, but when we tried to do it, we realized there were other problems with that. The CVE entries are not classified by CWE. Vendors, if they use the CWE, they use different levels of abstraction. So if a vendor reports on a very high level kind of weakness, and we're trying to separate the issues at the lower level, we're not sure to which one of those the data applies. So this year we had some uncertainties and variability because of that, and that's something to improve for next year. There were other ideas being discussed. People want to give more weight to, more importance to weight, more weight to importance or prevalence. They wanted to change the scale, right, the numerical values for each of the categories. So that led to interesting discussions. All right, so the top 25 list starts with guidance for different kinds of users. You say if you're a programmer new to security, you could do this, look at this first, and try to learn about this. If you're experienced in security, you can use a different ranking of the weaknesses. If you're a project manager, you can use this table and you can use this section and so forth. So for software testers, software customers, and educators, there's different guidance. So really, it's not just a list. There are several different sections in it and figures. Also new, we have mitigations. For example, I mentioned earlier the inputs. Same thing for the outputs. You want to stay in control over those. You want to lock down your environment. You should assume that external components can be subverted and that your code can be read by anyone. And you should use industry-accepted security features instead of inventing your own, because they're tricky to get all right. So if you try to do them yourselves, there's a great risk that you'll miss one little detail. And then at the end of that, there's a mitigation matrix, which shows if you want to defend against this kind or that kind of weakness, then you can use this mitigation, and that's going to be highly effective or will have just a limited effectiveness. We also have general practices in the list. For example, you should use libraries and frameworks that make it easier to avoid introducing weaknesses. You should integrate security into the entire software development lifecycle, because it's more expensive if you do it at the end. It's more difficult. A lot of people give up, right? They develop a software product and then they say, you know, what if there are vulnerabilities in what we've done? Then they bring in a consultant, and then you start getting a list of all that's wrong with the software. The cost of fixing that at the end is much, much greater than if you were doing it from the beginning. And chances are you're not going to be able to fix everything. Also, you should use a broad mix of methods to comprehensively find and prevent weaknesses. Code scanning is one example. Code reviews is another. So this is the list we ended up with. Number 1, cross-site scripting vulnerabilities. Now, I was debating if I should have started, when, like they do in shows, start with number 25 and build the suspense up to number 1. But I'll present them to you in the order they are. So cross-site scripting, it's a weakness in web applications. SQL injection, when attackers can add extra commands when commands are sent to a database. Classic buffer overflow, that's more specific than what we had last year. Cross-site request forgery, I mentioned it earlier, that's also a web flaw. Improper access control. Untrusted inputs in a security decision, right? An example of that is when people store privilege information in a cookie. And when they retrieve the cookie for the web application from the browser, they trust the values in it. For example, administrator equals yes. Okay? So that's an untrusted input used in a security decision. We'll grant you all administrative privileges if you change no to yes. Path traversal. Right? If you're doing FTP, you're trying to download something and you try to have access to other files in the operating system. Unrestricted upload of dangerous file types. Let's say you have a website encoded in PHP and you're allowed to upload PHP scripts. Maybe then you can't get them to be executed. OS command injection. That can happen a lot when you have complex systems that are built with different computers and you want to send command to another server and you use SSH to do it over there, and then you compose a command, and inside the command you do string concatenation, right? And you use an input inside. And this input was not validated. So someone can add additional commands inside what you wanted to send to that server. Missing encryption of sensitive data. We talked about that earlier. Use of hard-coded credentials. We also talked about that. Buffer access with incorrect length value. That's a new one. PHP file inclusion. That's when you have a web application and the path for the inclusion of the PHP files can be changed by an attacker. And the attacker can specify a remote site, because PHP is so powerful and helpful that if you specify a URL instead of a local path, it will happily go get that URL, the file specified by that URL on a remote server and execute it in your web application. Improper validation of array index. That's a more specific form of. Everybody can guess. Buffer overflow. That's right. Improper check for unusual or exceptional conditions. You have something going wrong in a script running with elevated privileges. You don't check for errors. Maybe what went wrong is that your system got attacked and you don't realize it and you happily continue in a compromised environment. All right, integer overflow or wraparound. Right, that's when you're trying to do an operation on, let's say, a short, and the result of that operation is greater or smaller than what the short can represent. Incorrect calculation of buffer size. That's again a more specific case of buffer overflow. Missing authentication for a critical function. That's when maybe you have a function that only administrators know about, or it's only called in your code. It's only called by other code that you trust, but you don't realize that it's exposed. Other people can call it. It can be part of an API. You want other people to interact with your system. We talked about download of code without integrity check. Permission assignment for a critical resource, that's obvious. Allocation of resources without limits, or throttling. That's obviously when you can make requests that are very expensive for the server, but cost very little for the attacker. URL redirection to an untrusted site. It's also called an open redirect. That happens when you have a web application and you're trying to count the clicks. Maybe you want to do attribution, you want to know how popular a file is or a resource is. Maybe there is some sort of scheme that redistributes revenue, advertising revenue, for example. So whenever you click on an image or a link, it goes back to the same website, which records the events and then sends you off somewhere else. Now, that function of sending off somewhere else, if it's open, if an attacker can specify that, then an attacker can give you a URL that looks quite fine. Let's say you see that URL on a forum. It starts with google.com blah blah blah. Oh, it's a search to find the things he was talking about. But instead, it's a redirect to a malicious site using a Google redirect. They don't do that anymore, but at some point they did. Use of a broken or risky cryptographic algorithm. That's fairly obvious. And then the race condition, which is when you check for something and then you're going to do something else, but in between, the validity of the check can change. So the action could be incorrect, become incorrect in the meantime. All right. There's more. There are profiles. So those profiles are different organizations of the CWEs for different kinds of applications. We can even include CWEs that were not in the top 25. For example, there's an educational profile. It includes the uncontrolled format string, CWE 134, because it's historically been important and it's a useful concept. Also, when we teach people about those, it's because we don't want format string vulnerabilities to be coded by our graduates. So there are additional considerations in each of those profiles. So for the educational profile, that's what I focused a lot on this CWE effort. We use a broader time for prevalence, all historical data that's available. Whereas the CWE itself focuses on just the most recent data. Again, that's because we don't want graduates to repeat mistakes that have been fixed and recognized in the past. I added an emphasis rating based on the difficulty of understanding and the usefulness of a CWE for understanding other concepts. So also added a little bit of consideration to how prevalent some mistakes can be by new programmers in the classrooms or in projects. Importance in producing good software engineers, the impact of the weakness, etc. So the final ranking is, again, importance times prevalence plus emphasis. Keep it simple and consistent. Other profiles that are available if they interest you. There's on the cusp, that's a list of those weaknesses that almost made it to into the list. So if you already mastered all the first 25, you can look at those additional ones which we think are, matter. There are weaknesses by language, only considered 4 languages. Weaknesses that are fixed typically in design versus implementation. Yes?
Which 4?
Which 4? I'll have a table in a few slides that will show which 4. Automated versus manual analysis of the code. And then for established secure developers, the rankings were done only using data from large companies, which have internal training programs and so forth. They can also be ranked by importance. If you're contracting out the development of software for your company, then you may be more worried about the importance of weaknesses. That is this angle. By technical impact, that is a ranking by the consequences of those weaknesses. Here's an example. Weaknesses by language. That's only the top part of the table. So we have C, C++, Java, PHP, and Perl. You can see that the ratings can vary. Sometimes we don't have any ratings. So for example, for PHP file inclusion, it's obviously specific to PHP, although you might contrive a way of making it happen in other programs. It's not something that other languages are predisposed for. So you can see, for example, one that's equally difficult for all the languages. It's to prevent SQL injection. Or equally easy if you know the solution and you're using prepared statements. All right, let's move on. Things that are fixed in design or implementation. A lot of things depend on how you implement them, but there's also a fair number that depend on how you design your system. And of course, you want to fix things that you can fix in the design while you're designing it, because it's more expensive to fix them later. So that gives you an indication of which weaknesses you should look for when you review your design or when you're at the implementation stage. OS command injection, that's often an implementation issue. Can you think of something that needs to be fixed in the design? And the hint is that we talked about it earlier. No, that's not a design issue. Pardon me? Validation of input. It could be a design issue if you think about using libraries and frameworks that automatically do it. Yes. One we talked about earlier was missing encryption of sensitive data. If you haven't planned for it, it's hard to implement it. Another example is using a risky or broken encryption algorithm. All right, another profile, automated versus manual analysis. The idea is to rate for each CWE, what is your chance of success if you use a white box approach versus a black box approach, and depending on whether you're using an automated versus a manual analysis. Right, automated means using a code scanner, and manual means doing things like code reviews. So, for example, reliance on untrusted inputs in a security decision. If you try an automated method, it's going to be fairly difficult because the code scanner will have difficulty figuring out which of the inputs are used for security decisions. So you'll have more limited success. If you're just given a black box, you don't have access to the source code. If you do a manual analysis, that's going to make it more difficult to figure out what's going on. But if you're given all the code in the white box approach, then it's easier to do a code review. All right. Here's a little bit of the table for weaknesses by technical impact. So they were rated for code execution, information leaks, also called exposures, privilege escalation, bypass of authentication mechanisms, and denial of service. So if you look at PHP file inclusion, you really should worry about the execution of additional code. It may be used for a denial of service, but if you have full access to the machine, why would you bother with just a denial of service? Okay. All right, things you can do with that top 25 list. So you can make sure you know what they are, so you recognize them in your code, and maybe in someone else's code when you do a code review. You should know the mitigations too, so you can apply them while you're developing the code. If you want to learn them, then you should have a look at the educational profile and the guidance for educational users. If you're doing auditing or penetration testing, then you may consider that list of weaknesses as a suggestion as to what may impact your application the most, what brings the greatest risk. Of course, you need to put it in the context of what the application does. Another thing you can do with it is to map each entry with what is being done in your organization. We want to try to figure out if the combination of all the things you're doing and the education and the libraries you're using and so forth allow you to prevent all of those weaknesses. So can you catch all occurrences of those weaknesses? So you could do code scanning, you could choose architectures, you could have code and design reviews, you could have a lot of testing, for example, fuzzing, or use random inputs and try to get the application to go into a state where that's unexpected, a state that's inconsistent. Maybe the application stops executing, or maybe strange things happen. It gives information, reveals information to attackers, and so forth. For example, Microsoft has mapped the CWEs to what they're doing in the SDL, right? That's what they call the security development life cycle. So, for example, about buffer overflows, buffer copies without checking the size of the input, they have educational material about that. They have a manual process that should catch them. They also use libraries that they design to be resistant to that, and also take care of the little details, making sure that when you do string manipulations, you're not going to overflow the string buffer. And so on for all the different weaknesses. And your goal, of course, is to make sure that there is one of the processes you're using that is going to catch the weakness. If you want more details about that, you can go on Michael Howard's site. So this year we got some tweaks to the CWE as a result of making the top 25 list. We got new entries created. The hierarchy was changed a little bit. We added a link, making CSRF an authorization problem, not just an authentication one. So there's nothing like using something you make yourself to find issues in it. The advantages of this new format we have a more consistent level of abstraction. We have an increased number of more precise, actionable weaknesses. We have customization for different classes of user with profiles. We have a lot more help and material around each of the weaknesses, and we have tables and guidance. If you take this new top 25 list, it's almost a crash course. It's like a crash course in secure programming. So it's a very helpful resource if you have new hires. You may want to get them to pay attention to it. So in conclusion, that was a much greater effort than last year. I think the list is going to be more useful for risk assessments. And we also found a lot of things that need improvement, such as getting data for prevalence. So that's it. We have time for a number of questions. Yes, Spaff?
So this list has been done in some form for several years now.
No, this is the second year.
Well, there was one before that just SANS did, right? That they're
Yeah, they had a top 20 list. Yeah.
yeah. I'm just curious whether anybody sort of looked at the trending over that to see if things that have been identified several years running as high priority problems are becoming any less prevalent, or are we still seeing them? As a matter of, are these lists doing any good?
So you're in a way asking if the list has had the measurable effect on the types of vulnerabilities that are found and the mistakes people do. One problem we have before being able to answer that is the issue of measuring prevalence. As I mentioned before, people don't report things as being at the same level of abstraction in the CWE if they're even using the CWE. Going back over the years would be a gigantic effort in categorizing incidence data for each of the types of weaknesses. So I'm afraid that at this time we don't have the answer to that. However, it's something that is very interesting and something that I've thought a lot about. So if we can get the measurement of prevalence more standardized, that will be a great help. However, you can already see that you can see some of the changes by which entries disappear and which are included. It's a little bit risky to try this direct comparison because the criteria have changed year by year, going from SANS to the first year of the CWE and the second year. But if we go back to some slides back, I've highlighted the weaknesses that were not there in last year's. They're in, those that are in italics were not there last year. So at a rough level, you can see how some of the changes happen.
Well, just to explain the reason I asked the question is that it's obvious a great deal of effort has been put into this. And there's also been a push by, primarily through SANS, I think, but trying to get contract language written or even government legislation requiring that the companies not be held liable if these top vulnerabilities show up in their code, or forcing schools to teach these in the programming curriculum. And I'm just curious if there is any hard evidence that any of that would do any good, if any of this effort or these requirements actually have had a measurable impact or would, or whether there'd just be another top 25 that would bubble up to take their place. And I know that's a question you can't answer directly, but that's really at the heart of why I'm asking the question.
Right, right. And really, I hope that in the coming years, we'll be able to answer that. I mean, we just have anecdotal evidence that it has an impact. For example, all the people talking about it and the interest. Yes.
Just out of curiosity, how do you rank one vulnerability over another vulnerability? So, for example, why would buffer overflow, why does that rank higher than cross-site trust coordinator, for example? Is it, you said you can't really measure prevalence of them. Is it
It
based, opinion-based or polls or researchers or?
Well, for prevalence, we did have some data. The point was that it was not as good as we would have liked it to be. So we do have, from the security vendors, for example, we have data about how often they found those vulnerabilities internally and externally as for consulting. So this year for prevalence, we essentially tried the best we could to merge all of the data in a consistent way. Again, it's not perfect, but we did end up with a rating from 1 to 4 for prevalence. And we also had a rating from 1 to 4 for importance. And then we multiplied importance by prevalence. That gave us a score. And if you look at the list, the score is listed also in one of the columns. So you can see, for example, how close two issues were or how far apart they were. So even though the ratings were somewhat coarse, there were many people involved in the rating process this year. So the hope is that by averaging over the ratings of many individuals, we're going to get to somewhere closer to the truth of how these weaknesses should be ranked.
Well, thank you very much.
Thank you. My pleasure.